Thank you, Dennis, and thank you for inviting me here. This is actually my first visit to IHES, and it's very nice here. So since I was already busted once, I gave this talk at the Clay Math Conference in the fall. So if you were there, you've heard this before, and I apologize. Anyway, this is a kind of an evolving project with a lot of aspects that's Arvind Azak and Jean Fazel and I are working on about approaching the problem of constructing algebraic vector bundles using methods of homotopy theory, and especially approaching the problem of trying to give a topological vector bundle an algebraic structure. So I want to, the context will be varieties just over the complex numbers, and the basic question I have in mind is which complex vector bundles have algebraic structures, like I just said. Now that is a really hard problem. That's a positive solution of that would imply the Hodge conjectures, even just in the case of affine varieties. So I'm not going to talk about this problem in general, but I'll eventually focus on the kinds of varieties that are as far away from the Hodge conjecture as you can get, where all the integral cohomology is of Hodge type, and hopefully say some interesting things about that. So this story and this interaction really goes all the way back to Sayre's conjecture and to Sayre's FAC. Oh, I don't know why that background got so dark. In that paper, Sayre's exploring this relationship between vector bundles on a space and finitely generated projective modules over the ring of functions on the space. So if there was a topological space, those would be continuous functions, and it was an algebraic variety or an affine algebraic variety. That's just the ring of algebraic functions. Sorry, something happened. Well, I apologize that that background is so dark. I just changed it and it changed back. Anyway, so in that paper in FAC, Sayre writes, it's not known if there's any when X is just affine R space, if there's any finitely generated projective modules which are not free. And of course, he's thinking by analogy with topology, where vector bundles over a contractible space are all trivial. And this became known, of course, as Sayre's problem, even though it was just a question. And eventually it became known as Sayre's conjecture. I guess Sayre has that kind of karma. And that problem was solved independently in the 70s by Quillen and Suslin. So the theorem was exactly that if K is a field, every finitely generated projective module over K is free. Just give me 1 second. I don't know why that is so dark. Oh, it'll lighten up in a minute. All right, so these are just going to be dark. All right. Okay, so as we said, blah, 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 solved independently by Quillen and Suslin in this case. All right, and so there was a whole bunch of problems like that, and many of them promoted by Hyman Bass and Sayre and others. And Adams kind of identified in his math review of these papers, he identified an ongoing program. This shouldn't imply that this was Adams' program, but he articulated it in this math review saying, well, I know you can read that, but he says it leads to the following program: take definitions, constructions, and theorems from bundle theory and express them in terms of finitely generated modules over a ring, and then use bundle theory as a conjecture generating device and try to prove these things about rings. And one of the maybe one of the most definitive conjectures along these lines is what's known as the Bass-Quillen conjecture. And that concerns, so I'm going to be looking at vector bundles in various categories, and so I'll just write vect K for the set of isomorphism classes of rank K vector bundles, and then decorate with algebraic, topological, or whatever. And so the basic thing about in topological vector bundles is they're homotopy invariant. The set of isomorphism classes of a vector bundle over a space cross an interval is the same as the isomorphism classes of vector bundles over the space. And the Bass-Quillen conjecture asks that that be true if that's true for algebraic vector bundles. And I think you need some hypothesis. And I think the most general form of the conjecture I know of is that when A is a regular ring of finite Kroll dimension, then every finitely generated projective module is extended from A in the sense that I wrote. So that would be the exact analog of the thing in topology, that vector bundles are homotopy invariant. So as far as I know as well, this problem isn't solved in general, but in 1981, just building on the Quillen-Suslin proof, Lindell showed that the Bass-Quillen conjecture was true when A is finitely generated over a field. So that's called the geometric case. And if you're interested in this and you don't know about it, T.Y. Lamb has a wonderful book on this Serre's problem on projective modules. So this leads, if we really take Adam's articulation of this program seriously, it leads to this question: can we study algebraic vector bundles using homotopy theory? It was sort of a lot of conjectures and theorems were setting up the basics of doing that, but what would happen if you really tried to go the distance and really try to use the methods of homotopy theory to study algebraic vector bundles? So now abstract homotopy theory comes in and lightens everything up. So in order to do that, we have to have an abstract framework for talking about homotopy theory. And so, I mean, this has come up in 2 of the 3 talks already today, but I'll also review it a little bit. So in the setup for abstract homotopy theory, I mean, it probably really also starts with Grothendieck, but it sort of starts to take on an apparatus of definitions in the work of Dan Quillen and Dan Kahn. Quillen, of course, had found himself doing homotopy theory in many different contexts, and he wanted to prove that different approaches to the same homotopy theory were the same. He wanted to prove that differential graded algebras modeled topological spaces up to rational equivalence, and differential graded Lie algebras and coalgebras and all that, and he needed an abstract framework for making sense of that. And there's a lot of, and Dan Kahn spent most of his working career kind of boiling this notion down to its essence. And nowadays, at least in algebraic topology, we think of you think of the basic arena of abstract homotopy theory as just consisting of a category and a subcategory of morphisms that you intend to identify as equivalences. So the language the terminology is borrowed from homotopy theory, but you're really just localizing, or in some sophisticated sense, just the way Serre localized abelian categories. So in this language, you have a category and a subcategory of weak equivalences, and you consider functors called homotopy functors that take the weak equivalences to isomorphisms. And there's a universal homotopy functor that's characterized by it's almost the obvious universal property. Given a homotopy functor, there's a unique functor making the diagram commute. If you're kind of thinking about categories or higher categories, this might seem like kind of a rigid thing to request, because you're characterizing an arrow in a 2 category, and so it should only be characterized up to a contractible groupoid or something. But the difference between this rigid thing and perhaps the more complicated but natural higher categorical statement is just the one of asking that the objects of the homotopy category be the same as the objects of the category. Anyway, that was just me editorializing. It's not going to play an important role. There's a universal homotopy functor. I keep losing this. So the classical example is topological spaces, and the class of weak equivalences are the ones that induce isomorphisms of homotopy groups. at all possible choices of base points. And that becomes classical homotopy theory, and the homotopy category is the usual homotopy category of CW complexes. So I'm just mentioning that just to kind of locate the origins of the terminology for you, but also to introduce some notation. Nobody really in their right mind ever writes out that symbol, and usually it's abbreviated with square brackets. So whenever, in all these worlds contexts where I'm going to talk about abstract homotopy theory, I'll just use square brackets and some subscript to indicate the context. All right, so homological algebra also gets absorbed in this abstract homotopy theory world. In fact, Quillen called abstract homotopy theory homotopical algebra. Oops, I got ahead of myself, but maybe it doesn't matter. There you take the category of chain complexes, possibly bounded below, and the weak equivalences are quasi-isomorphisms, and your intention is to only study functors that send quasi-isomorphisms to isomorphisms. So as far as doing homotopy theory with algebraic varieties goes, I think the first place that's set up and kind of the framework's laid down is in the thesis of Ken Brown. I didn't put a date down, but that I think also goes back to the late 1970s. And he has his thesis was published in a paper called Abstract Homotopy Theory and Generalized Sheaf Cohomology. And really the main thing there is he wanted to set up a world where sheaf cohomology was homotopy classes of maps into some kind of an Eilenberg-MacLane space suitably defined, and to be able to talk about generalized cohomology like we do in homotopy theory. And so this isn't precisely the category he set up, but it's convenient and it connects better with the ones I want to talk about. So I want to consider the category of smooth varieties over the complex number, and I'm sorry, that's the basic Grothendieck topology, or that's the basic category, and I want to just consider the category as simplicial presheaves on that. So contravariant functors to simplicial sets. And so that doesn't have anything to do with the notion with recovering. I mean, you want to recover. You want some sort of local to global principle. You want to recover the sense in which your smooth variety was built out of smaller pieces. And so you add, you don't impose that relation in a sheaf condition. You add that to the weak equivalences. So the weak equivalences are the original simplicial weak equivalences, and then for a technical reason which plays a role throughout the talk but won't play a role at the level of detail I'm giving, you use the Nisnevich topology. So the weak equivalences are the Nisnevich hypercoverings, which expresses the way in which local things accumulate to global things, and the simplicial weak equivalences, which is what was the whole point of putting in the simplicial presheaves. So this leads to what you might call what I'll call algebraic homotopy theory, and I'll decorate that with an alge. And this is, in this world, you can formally put in Eilenberg-MacLane objects for any sheaf or presheaf, even of abelian groups, and calculate hypercohomology or sheaf cohomology in terms of the homotopy category. Okay. And then there's motivic homotopy theory. So that's basically the same, except you take the algebraic weak equivalences and you force the affine line to be contractible. So we take now we want to add to the weak equivalences all those maps, the projection maps from the product of any x with the affine line to x. And so that's motivic homotopy theory. So an invariant of algebraic studying homotopy functors on the algebraic category would just be things like sheaf cohomology, and systematically studying homotopy functors on the motivic category would be studying things that are A1 homotopy invariant in a systematic way. So there's what you might call realization functors. The motivic equivalences contained the algebraic equivalences. So for formal reasons, there's a functor from the algebraic to motivic homotopy theory. And over the complex numbers, since the affine line is contractible in topology, there's also a realization functor to topology. I might have, maybe a better notation would have been C upper an, because it's the underlying analytic. It sends a variety to the underlying analytic variety. Okay, so that's the basic setup of abstract homotopy theory, and I said the question was, can we study vector bundles in that using abstract homotopy theory? Oh, sorry, we're back in the dark again. This'll, whatever. All right, so in, yeah. So I thought I was to change all of them to light. I didn't really mean to say, you know, only the discussion of abstract homotopy theory is going to have a light background, but hopefully that'll go back. Okay, so so in topology, if you have a group, there's a classifying space for principal G bundles, and Siegel introduced this simplicial definition, which I think is probably familiar to everybody. And in topology, principal G bundles up to isomorphism is given by homotopy classes of maps into BG. So the problem of writing down the set of isomorphism classes of k-dimensional vector bundles is the problem of determining the homotopy classes of maps into some classifying space. And the same thing is true for formal reasons in the Ken-Brown algebraic homotopy theory. I'll say more about that in a minute, but that really just unpacks to the local description of vector bundles in terms of charts and transition functions. And so you also have a statement like that. There's a universal vector bundle, and vector bundles becomes a homotopy problem, but homotopy doesn't involve deformations parametrized by the affine line. So anyway, with that in mind, let's just abstractly define motivic vector bundles to be the set of maps in the motivic homotopy category from X to BGLK. So right now that's just an abstract definition, and there's the realization maps between those categories give me a map from the set of isomorphism classes of algebraic vector bundles to the isomorphism classes of motivic vector bundles, and then to topological vector bundles. Okay, and so one can study the problem of, take the problem of giving a vector bundle on a topological, on the analytic variety underlying a complex projective variety. One could take the problem of finding an algebraic structure on it and ostensibly factor it into two separate problems. But in fact, there's a good relationship between these so let me turn to. So the first thing is there's a theorem of Morel. So Morel's published his theorem in 2012, but I think it goes back quite a bit before that. And then Marco Schlichtling, and then later Arvind Azak, Mark Oiwa, and Matthias Wendt found a much simpler and more direct proof of this theorem. But the theorem says that for smooth affine varieties, this map, the map from algebraic and motivic vector bundles are the same thing. And you can think of that as a sort of really definitive version of Lindel's theorem, or even the Quillen theorem. That Lindel's theorem saying that at least this has a chance. Lindel's theorem says that algebraic vector bundles is A1 invariant, and anyway, this is kind of it's a improvement of Lindel's theorem, and in some sense the more definitive statement that you might wish for. Okay, so that's the case of smooth affine varieties. For projective varieties, there isn't really much of a chance. The set of isomorphism classes of algebraic vector bundles on projective varieties isn't even deformation invariant. So I wrote down an example here, but which is sort of pretty elementary to say, but just take a, if you take a, O of 1, well, take the Euler sequence on P1, so that writes O of 1 plus O of minus 1, or as an extension involving, I'm sorry, that writes the trivial bundle as an element and as an extension of O of 1 by O of minus 1. And now just move the xth class in a straight line to the origin. I just wrote down an explicit way to do that. And that gives you a deformation from O of 1 plus O of minus 1 to the trivial bundle. So probably everyone in this room knows that kind of thing very well. Anyway, so that set is not A1 invariant, and so there's sort of no hope really to describe. It doesn't. I mean, it's sort of a non-starter. You're not going to describe algebraic vector bundles in terms of motivic homotopy theory. However, so this is a question I don't really know the answer to. I don't really expect this to have a positive answer, but I don't really know the answer, and that is. The most naive answer would be that's all you do. The set of motivic vector bundles is just algebraic vector bundles modulo the equivalence relation generated by identifying a vector bundle over X cross A1 with its fibers over 0 and 1. This seems quite strong to me, but I don't really know a counterexample to it. And you'll see this would have a lot of, so this would imply, for instance, that every motivic vector bundle had an algebraic structure. And again, I don't really know a counterexample to that either, but, and in some sense that's going to be the main thing I'm talking about. But anyway, I'm putting it up as a naive guess. I don't really expect that to be true, but it would be nice to even know, to understand this quite a bit better. Okay, so nevertheless, there's something you can do by exploiting Xuan-Gottfried's device. So so here's the easiest example I know of to explain it. Take affine n space minus the origin. So that's defined by kind of algebraic inequalities, and that's not a affine variety. But if you give an algebraic reason for the x's to not be 0, so if you take this ring, you add some y's so that that sum is 1, then that is an affine variety, and that's a torsor for a vector bundle over affine n space minus the origin. And so it's a weak equivalence. And then if I modded out the evident action of the multiplicative group, then I would get a bundle of affine spaces over projective space. And in fact, and then you can restrict to closed subgroup. In fact, there's a quite general story here, but if you have a quasi-projective variety, there's always an affine space bundle where this J of x is an affine scheme. And that J of x is equivalent to x in the motivic homotopy category because those affine spaces are contractible, and it's also smooth if x is smooth because it's a Zariski locally trivial bundle. Okay, so anyway, the upshot is every smooth variety is weakly equivalent to a smooth affine variety. And so the problem of whether a motivic vector bundle has an algebraic structure is equivalent to a purely algebraic problem, because motivic vector bundles on X are the same as motivic vector bundles on the Xuan-Gottfried device, and those are the same by the theorem of Morel and Azak and Oiwa and Wendt to vector bundles over the Xuan-Gottfried device. And so the question I was asking is sort of really comes down to the question of whether vector bundles on Xuan-Gottfried devices extend to the base space. And I don't know an example of one that doesn't. It's easy to find the descent. Vector bundles can descend in many, many ways, but and anyway, it would be nice to have hands on an example of one that doesn't descend. But okay, all right. So that's a little bit of a tour of the easy relationship, or sort of the known relationships between algebraic, motivic, and motivic vector bundles. And so now when I say I want to study vector bundles doing homotopy theory, what do I have in mind? Well, so in any abstract homotopy theory, anytime you set it up, it comes to you with its own kind of internal notion of homotopy groups and its own kind of internal notion of cohomology. And there's a Steenrod kind of obstruction theory you can always, that sort of also always, you can always exploit, and it always relates the ith cohomology of X with coefficients in the ith homotopy group of, oh, that's supposed to be an X, to maps in the homotopy category from X to Y. So in algebraic homotopy theory, if we were to look, so this obstruction theory gives you an idea of what these how these categories are kind of digging into the theory of vector bundles. And so this gives you another way of seeing why the algebraic homotopy theory is, it's just a formal, it's really just kind of formal. The homotopy groups, or the homotopy sheaves of BGLK are just GLK when I is 1, and they're trivial otherwise. So this just becomes the statement, the obstruction theory just becomes the statement that vector bundles is H1 with GLK coefficients. So there's nothing, that doesn't penetrate into the theory of vector bundles at all. On the other hand, motivic homotopy theory does. So the fundamental group of BGLK in motivic homotopy theory is GL1, and pi 2 is the second Milnor-Witt unramified Milnor-Witt K theory, and there's a little bit of information known about the higher homotopy sheaves, but it's a little complicated, and it does lead to an interesting obstruction theory.
I'm sorry, pi 2 of BGLK? Pi 2.
Oh, pi 2 of BGLK. Yes, thank you. I'm sorry. Yeah, thank you. Yes, not 2, right. Yeah, and I probably need K to be, yeah, at least 3 or something. Yeah, sorry about that. Thank you. So I want to talk about this obstruction theory for a minute, but so this obstruction theory, this will apply if you're studying vector bundles over smooth affine varieties. And that was something that was studied pretty intensively by Griffiths and others in the 1970s using analytic methods. So Griffiths' idea was you take a complex vector bundle by Grauer's theorem has a unique holomorphic structure, and if you can give and so you have a holomorphic connection, and if you can make that connection algebraic, you have an algebraic structure. And so he studied, using value distribution theory, the growth rate of the connection form as you go to infinity, and he found kind of a series of obstructions to algebraicizing vector bundles. And these give you a different series of obstructions that are very homotopy theoretic and very kind of discrete feeling. And one of the things we haven't really worked out, but I think would be really interesting, is to understand the relationship between the cohomology with coefficients in these homotopy sheaves and the value distribution theory that Griffiths was looking at. Because they're not, I mean, anyway, they're not obviously related to each other at all. So Morel and Azak and Fasel investigated problems of splitting free summands off of projective modules over regular rings in low Kroll dimension using these methods. And Jean and Aravind and I, this was sort of more a proof of concept at this point than anything. So the other thing from that era in the 70s was a sort of philosophy. I don't want to call it really there was just a sense that if the Chern classes of a vector bundle were algebraic, the bundle was algebraic. And that's probably because that program was designed to get at the Hodge conjecture, and the idea was all they wanted was the Chern classes to be algebraic. But so we sort of dug into this and just produced an example of a smooth hypersurface in P1 cross P3 for which the complement has algebraic Chern classes, but it's not algebraizable. And I think this would be, we haven't done it for this example, but I think this would be a really interesting one to see why, from the point of view of value distribution theory, that this bundle, this rank 2 bundle, doesn't have a algebraic structure.
Is it stably algebraizable? That is, if you make it the rank big enough?
If you make the, yeah. This is important that it's two-dimensional. If I make the rank bigger, it'll become algebraizable, I think. I think that's right. Yeah, I think that's right. Is that what your question was? Yeah. Okay, so as I said, so that's a little bit of a tour of kind of one thing that's going on. But where we're starting to see some interesting progress is in kind of the kinds of varieties that are as far from the Hodge conjecture as you can be. So that's the problem of defining algebraic vector bundles on projective space. And line bundles, we know, so the first interesting problem is to classify the rank 2 bundles on projective space. And that's, of course, a very famous problem. There's Hartshorne's conjecture, which says that if n is greater than 5, every rank 2 bundle is a sum of line bundles. And there's something, I'm going to mention it because it plays a role in the story I'm telling. So I don't know what to call this. I'm going to call it the Grauer-Schneider problem. And it says that every unstable rank 2 bundle, unstable in the Mumford sense, every unstable rank 2 vector bundle on Pn is a sum of line bundles. So that's for n4 and on. And I'm calling it a problem because it was a paper, and then shortly after the paper was published, there was a mistake found, and the proof has never been repaired. But it impacts, the timing of that paper impacts the story I'm telling. Okay, so if the Chern classes are 0, that implies the vector bundle's unstable. Now, so in the 1970s, this Hartshorne conjecture was around, the Grauer-Schneider theorem was a theorem, and so then the question turned to some topologists, produce some topological vector bundles with no Chern classes, for instance. And so Larry Smith did it, Elmer Rees did it, and Bob Switzer kind of made an elaborate table of vector bundles, topological vector bundles on projective space through a range of dimensions. And I think these are all rank 2 bundles. So Elmer Rees, using homotopy theory, constructed some rank 2 vector bundles on Pn with no Chern classes. And at the time of writing, those were examples of topological vector bundles with no algebraic structure. And but now, the current state of the art is there's still no known example of a topological vector bundle on projective space that doesn't have an algebraic structure. And one question we might ask is, was that wrong? Do the Rees bundles actually have algebraic structures? Now, okay, so let me tell you a little bit about the Rees bundles. So in topology, you study the homotopy classes of maps into BU2 in terms of the cohomology of projective space with coefficients in the homotopy groups of BU2. And those are, by the long exact sequencer, or the fact that, whatever, those are the homotopy groups one dimension down of U2 or SU2 or S3. So what you meet when you try to understand rank 2 topological vector bundles on complex projective space are the odd homotopy groups of the 3 sphere. Now the first odd homotopy group of the 3-sphere, if at the prime p, is in this dimension, pi 4p minus 3. And Elmer-Rees just took that element and made the obvious vector bundle. So you take this complex projective space of that dimension, 2p minus 1, collapse out the lower dimensional projective space to get a 4p minus 2 sphere, and go over by this first, by a chosen generator of that group. And then Elmer-Rees proved that these were non-trivial for all p. He determined to what larger projective space they could extend. He answered the kinds of questions you would want to know about these. And those bundles, of course, have no Chern classes, at least for p something, 3 maybe, and bigger, because they vanish on the complex projective plane inside there. So that's predicted to have no algebraic structure. Okay, so those are predicted. And so now I want to go back to this sort of way I was setting this up and ask, do these bundles have motivic structures? And if they do, can we get those to have algebraic structures? And so in order to do that, we need to kind of see if we can do the same homotopy, the same kind of, we need to study the same obstruction theory in motivic, the motivic homotopy category. So in motivic homotopy theory, there's not just a Sn for every n, there's an SPQ. And I learned this stuff from Morel and Voevodsky kind of in the late 90s, and was taught to use these two indices. So the first one stands for dimension, and the second one is kind of what you can think of as the Hodge weight. Some people nowadays, and if you're one of them, forgive me, some people use a different convention on those. So the 1,1 sphere is GM, or the affine line minus the origin, and the 1,0 sphere, which you should think of as really just combinatorial, is the affine line mod 0, 1. And since the affine line is contractible, I mean, that's really just the circle in the simplicial direction. And more generally, SPQ is gotten by taking the smash product of these with each other. But the way these come up in more geometric questions is the affine n space minus the origin. That has dimension 2n minus 1, and there's a little bit of Hodge weight of n in there. And n-dimensional projective space mod, oops, that's supposed to be a Pn minus 1. That's the 2n sphere. Okay, so then there's motivic homotopy groups, and there's a topological realization functor, as before. And under that, these bigraded spheres, they just go to the underlying topological sphere of that dimension. And so there's a map from pi AB in motivic homotopy theory to just the ordinary group pi A. So what you're expecting when you look at this, the way you expect, so a lot of familiar elements in the homotopy groups of spheres lift to motivic homotopy theory. The pi n of Sn is Z. You can get the Hopf maps. But then there's a lot of more elaborate discussion things in homotopy theory where you're using the fact that some product of things is 0 and you're building some higher order product. And there's room in there for the Hodge weights, for there not to be a consistent way of lifting the Hodge weights. So what you're looking for when you're trying to show that something fails to lift from ordinary topology to motivic homotopy theory, sort of the only thing you have to look for is I think of it as kind of an elaborate refinement of the Hodge conditions. And it's somehow, I don't know a great way of expressing it, but what you're looking for is there not to be a consistent way of putting a Hodge weight into some construction. Now, I actually had prepared, I wanted to show you a construction of this element in pi 4p minus 3, but I can do that on the board later, but I decided not to do it. I've done it. It doesn't, I found it doesn't go so well in this format. But if you want to know about it, I'll tell you about it. But I want to tell you one deep theorem that goes into it. So you have to get started somewhere. And where you start in homotopy theory is with the element in pi 2n of Bu, the generator for the K theory of the 2n sphere. So that, by instability, comes from an element in pi 2n of Bun, or it's an element in pi 2n minus 1 of Un. You start with that element, and that element has degree n minus 1 factorial when you map Un down to the n sphere. So this is the key. You start with that, and then you do a bunch of things. And I just, so there's some tricks, some localization, there's sort of some boilerplate stuff in homotopy theory that you can imitate in motivic homotopy theory. But the key thing that gets you going is this map from this odd sphere into the unitary group. And that's provided in algebra by this beautiful theorem that was in Susslin's thesis called the n factorial theorem. And that says that if you have a unimodular row, a sequence of elements of a ring that could be the first row of an n by n matrix with determinant 1, no, you don't get to have it be the first row of a matrix with determinant 1, but if you raise the entries to enough powers where the products of the powers is n minus 1 factorial, then there does exist a unimodular matrix. And that's what gives you this element, this lift of this element in pi 2n minus 1 of Un. That's what makes that algebraic. So this mismatch between n factorial and n minus 1 factorial is just because I started counting with 1 instead of 0. But, okay, so anyway, you can use this secret construction, which I'm willing to tell you about, but I haven't told you about it. You can use this construction, and if you follow that, you wind up with a motivic lift of this first element of order p in pi 4p minus 3 of the 2 sphere. So that has order p, it's got dimension pi 4p minus 3, and it's got Hodge weight 2p. Now, if we go back and look at what we wanted to imitate Ries's construction by modding out a lower dimensional projective space. And that gives us, well, so the dimensions, trust me, they have to work out. The number to pay attention to is the Hodge weight. The Hodge weight was supposed to be 2p minus 1, and we got something with Hodge weight 2p. So the Hodge weight is wrong, and you might think that there would be a way of exploiting this to show that these don't lift to motivic vector bundles. So the theorem is they do. They lift to motivic vector bundles. And the reason is this element had finite order. And in motivic homotopy theory, there's this operator rho that lowers, you can lower the Hodge weight on the torsion in the homotopy groups. And it's pretty easy to explain what that is. So let's take that. I'm going to take the degree n map on S11, and I'm going to cone it off. So that Mn is the Moore space for the degree n map, or it's the mapping cone of the degree n map on S11. And I can, so I'm over the complex numbers, so I can choose just take a linear map in A1 that connects 1 to a chosen nth root of unity. And that gives me a map from the other sphere, S10, into this M11. Okay, so that's an operator, right? If I have an element in pi 11 or higher of order n, I can compose it with this and get an element in pi 10. And these are compatible as n varies. And what does this realize too in topology? So that circle is wrapping n times around the origin, and that line is my line from A1 mod 0, 1 in. And in topology, that's of course homotopic to just that arc, which goes once around the bottom circle. So in homotopy theory, this rho realizes to the standard inclusion that just says, so what operator is that? That starts with an element of order n and says, oh, that it was an element. I don't care anymore that it had order n. It's just restricting. So a map from the one thing is as an element and a null homotopy of n times it, and I'm just forgetting the null homotopy. Okay, so that gives you this operation realizing to the identity map. And that lets us lift the Riesz bundles to motivic vector bundles. So, so this is something, so these are rank 2 projective modules over that ring I wrote down, over the degree 0 part of that ring I wrote down. I have no idea how to write those down as projective modules. We know that if you add a free module to them, they become free of rank 3, but I don't know, we can't go through every step of the construction and produce those. And in fact, every vector bundle, every topological vector bundle, I know from Switzer's chart, from there, we can lift to vector bundles over the Xuan-gottfried device. So this method gives you, it produces a lot of new rank 2 modules over these, projective modules over this xuan-gottfried device. The problem of descending from the xuan-gottfried device to projective space, that could be where, that seems hard, and I don't have anything good to report on that. It could well be that we've traded one hard problem in for a different one, but these, but nevertheless, these, there's a lot of new rank 2 projective modules over these rings. So that's the idea. So that's the main result, is that at least the Riesz bundles, and there's a lot of new motivic vector bundles on projective space, but that wasn't really the main. That was part of the main thing I wanted to talk about. So I told you that where you're expecting something to go wrong in lifting something from ordinary homotopy theory to motivic homotopy theory is that the Hodge weights start to sort of, there starts to be something inconsistent about them. But there's this rho operator, and as soon as stuff starts to have finite order, you can shift the Hodge weight down as much as you want. And this makes one wonder if there's a way, a sort of general idea that might show that you can always lift things in certain cases from topological things to motivic homotopy theory. And there is, so this is a kind of hypothesis, I guess I would even think of calling it a conjecture, called the Wilson space hypothesis. And it takes something that I think is one of the best kept secrets in homotopy theory, and the conjecture is that the analog holds in motivic homotopy theory. So I'm just going to take a couple minutes and describe it. So in homotopy theory, there's this remarkable class of spaces we call even spaces. So they're even in the sense that their odd homotopy groups are 0, and they only have even dimensional cells. Now, that's simple. There's a whole bunch of really non-obvious things that come out of this. So for one, you know, it turns out that the even homotopy groups have to be torsion-free. So if the space has finite type, those have to be free abelian. That's not obvious from the definition. They turn out to be infinite loop spaces. And in fact, there's prime ones. There's a Wilson space, an even space that starts, there's sort of a minimal one for every even sphere. And I believe those have unique infinite loop space structures, and everything is built out of those. This theory, it has a remarkable rigidity. So examples of these spaces are infinite dimensional complex projective space. that's a KZ2, BU, the classifying space for the infinite unitary group, and BSU. So I want to just point out, we know these are even, the homotopy groups we calculate for some reason. The cell decomposition comes from algebraic geometry. I mean, we have algebraic cell decompositions for CP infinity, BU, and I suppose BSU. So the first example where you don't know anything like that is the fiber of the universal second Chern class. So in topology, that's called BU angle bracket 6, but it's not a very useful, I mean, that's a notation that tells you what it is, but it's not suggestive of anything else. But that space has only even dimensional cells, and I don't know an algebraic geometry reason for that. I'm sorry? It is even, yeah. Yeah, that's the first, yeah, that's even.
It follows from the theory that is not from just looking at flag varieties for BU. So
right.
It comes from what?
What are you asking? How do we know that's even? So what goes into that is knowing the Sayre spectral sequence and knowing the cohomology of the Eilenberg-MacLane space and the action of you use the Steenrod algebra, the Eilenberg-MacLane space, etc. So I'm about to ask the same question in motivic homotopy theory, where we don't know. I mean, knowing that's even would tell you the cohomology of KZ4. You can go back and forth. So it uses that.
No, but how do you know it has even set? Is it the first or the second condition that you are proving?
So it has even homotopy groups, that's obvious, right? It has even cells because I calculate its cohomology and I find it's free abelian and only in even degrees. So in topology, that's enough to have even cell decomposition. Okay. So Steve Wilson proved this amazing theorem that the classifying space for complex cobordism is an even space. So the fact that the first condition, that its homotopy groups are even, that's Milner's computation of the complex cobordism ring. This is a complete surprise. And in fact, that's true for every even suspension, positive or negative, of MU. And the Wilson space hypothesis that I want to make in motivic homotopy theory really involves all those suspensions. I just kept it simple. I kept the statement simple for these purposes. So so this also has a highly computational proof. It's been tricked out so that it's short now, but it's very, there isn't a known geometric reason. But there kind of ought to be. See, what is this zero space of the complex cobordism spectrum? You're supposed to think of that as the moduli space of zero-dimensional, stably almost complex manifolds moving through cobordisms. So if you really go through Thom's theory, these are zero-dimensional manifolds embedded in a big complex vector space, and as they move, they can transform through cobordisms. And I said it that way to make you kind of think Hilbert scheme. I don't know a real relationship between this and the Hilbert scheme, but there should be a kind of Hilbert scheme, some sort of stabilized Hilbert scheme-y model for this space. And the cell decomposition would just come from the torus action on the big affine space, just like it does for the Hilbert scheme of points in the plane. So there should be, so the topologists don't have a good enough geometric model for this to prove this theorem, but it would be, that would be one way, that would be something very, very useful to have. And it does feel like there ought to be, well, like I said, some variation on the Hilbert scheme kind of model. Okay, so now I can make I can ask about the exact analog in motivic homotopy theory, and there's a little bit of guessing, but I think the analog of those two conditions is that pi 2n minus 1n of x is 0 for all n, and that it has a motivic cell decomposition out of those spheres. So I stated that in kind of a clumsy way there. But let me just say, anything with an algebraic cell decomposition satisfies part 2. So P infinity, BGL, BSL, those are all examples. It's not known. The first one we don't know is the fiber of the universal second Chern class. So, for that, so that this one we don't know, and we don't have, and it's mostly because we don't know the cohomology of that Eilenberg-MacLane space, or of KZ of 2, 3. So that's one. This is the first one where we don't know if it's even. We do know. All right. So the Wilson space hypothesis is that that classifying space for algebraic cobordism is even. And I really mean that smash S2NN for any n. Now that's known to satisfy 1, so that was a theorem of Morel's and mine a long time ago, and I think there's been other proofs of that. Anyway, those groups of the motivic bordism spectrum are known to be 0. The other thing I want to make a comment of, I started talking about being over the complex numbers, and in all the proofs, I mean, I needed rho, so I needed to have some roots of unity. In particular, you could keep track of those. Probably need -1 to be a sum of squares for various reasons. But this theorem, so you could ask, is this true over the real numbers? Or is it reasonable to guess this over the real numbers? Then you would want the theorem in topology to be compatible with complex conjugation. So that Mike Hill and I have checked. So that's a theorem that in topology, that's true. The analog of this is true in Z2 equivariant homotopy theory. So I don't know if I think this should be true or not. I'm kind of willing to run with it. But the indication is that this would really be true. I think one would expect this to be true over Q, or maybe even over Z, if this. But I think, anyway, this seems like there shouldn't be a field of definition issue with this. Okay. So what the Wilson space hypothesis lets you do is build resolutions out of the motivic Eilenberg-MacLane spaces K, Z, N, 2N. So what you do is you take what topologists call the unstable Adams-Novikov resolution, and the Wilson space hypothesis says you're never leaving the haven of even spaces when you do that. And then the Voevodsky, or the Posnikov, or the slice tower for any one of those spaces is a product of these, or the associated grade is a product of these KZN, 2N. So you get a resolution in terms of specific motivic complexes. In ordinary homotopy theory, that's not such a big deal. Abelian groups can be resolved into free abelian groups at not much cost. But in motivic homotopy theory, the homotopy sheaves can be any strictly A1 invariant sheaf, and they can't always be resolved in this way. So that's the Wilson hypothesis. As I said, it lets you make a resolution that you wouldn't know how to make. And so I've been kicking this thing around for a while, and a couple years ago, or about 2 years ago, Igor Krish asked me about these complements of the discriminant variety, whether finitely generated projective modules over those are free. And if you run that through the Wilson space hypothesis, you find the prediction is that they are. And then Igor was able to find a pretty elementary algebraic proof of that. But this was, this isn't like, it predicted the redshift of Mercury or anything, but it predicted something. This was sort of a reality check for it. So the point of the Wilson space hypothesis is, so I put this theorem in quotes just because we haven't written down the proof, and it involves bringing a lot of sort of apparatus of homotopy theory into motivic homotopy theory that we understand how it should go, but I just put it in quotes because we haven't really written the paper. We haven't written it all down. But if the Wilson space hypothesis holds, then there's no difference between motivic vector bundles on projective space and topological ones. And that would actually be true not just for projective space, but for anything with an algebraic cell decomposition. So Grassmannians, blow-ups along linear things. I mean, all that sort of class of varieties with algebraic cell decompositions. There'd be no difference between motivic and topological vector bundles. So that would at least give you lots of vector bundles over these Xuan-Gottfried devices, and not, but then, you know, I don't know about the actual projective ones. So I think I've hit my time limit, but I'll just leave you with this diagram about this problem. So, you know, the Wilson space hypothesis implies this arrow is a bijection, and we can lift a lot of things to it. That gives you vector bundles on the Xuan-Gottfried device, and then the question about vector bundles on projective space becomes this possibly difficult problem of descent. All right, that's it. Thanks.
Are there any questions? Could you come back to the slide with the Wilson space hypothesis?
Yeah. That one?
Yeah.
That was the question.
Bizarre analogy.
Yeah,
So
yeah.
some question which I asked many years ago about kind of replacement of German normal form of matrices. You consider square matrices an action of PJ by conjugation.
Yeah.
And the question, can one make a collection if you count how many orbits on a finite field, for example, get sum of Q to length of partitions?
Yeah.
The question, can one make a collection of affine subspaces so that any orbit intersect exactly once this collection?
Oh.
And the answer is yes, it's pretty non-trivial, and it somehow smells similar to
It's serious. Okay.
a bunch of affine spaces and
I see.
making this.
You're trying to, yeah. Oh, that's. Is that in a paper then?
Yeah, somebody proved it, a few years ago.
Okay, I'll ask you later if you can help me find that. That sounds interesting. Yeah, it does smell similar. Thank you.
Any more questions?